Thank you, Katharina, and good afternoon, everyone. Unlike what you might expect, this will actually be largely an experimental talk. In fact, it should probably be given by Katharina and not by me, but as an organizer. She cannot talk, and so I get the pleasure and the privilege to talk about this recent work of ours on photon-assisted resonant Andreev reflections of photon-assisted tunneling in general at the atomic scale. So this talk will be mostly based on this recent Nature Physics publication, and the experiments, as I already mentioned, were let me get the laser pointer here. We're done in the group of, in Katharina's group, with her PhD student Olaf Peters being the main person. And the more detailed theory we wrote up in a separate PhysRefB publication. And here my students, Sergio Acero Gonzalez and Larissa Melishek, did all the important work. So, as we've already heard before the break, in many STM experiments on superconductors, it's very helpful to use superconducting tips that greatly enhances the resolution. So here, for example, are some data on Yu-Shiba-Rusinov states, once taken with a normal state tip and then taken with a superconducting tip. And clearly, the measurements with the superconducting tip have a much higher resolution and much sharper lines. So there reveals much more structure. And similarly, when probing Majorana bound states, for example, in these results of famous results of Ali Yastani, then the Majorana bound state comes in as a small bump when measured with a normal state tip, but becomes a more substantial feature when measured with a superconducting tip. Along with this higher resolution, though, comes an additional effort in order to interpret these results. And that is because tunneling between superconductors, even between plane superconductors, proceeds by a whole variety of processes. And one has to disentangle these processes. On top of it, of course, having so many processes also provides additional opportunities for getting information out of the sample. So let's start with the simplest such process, which is just single electron tunneling between, say, the tip and the substrate superconductor. That can happen by creating a hole in the tip and adding a quasi-particle to the substrate. So you're creating two quasi-particles in the system, so that requires a total energy of twice delta, or the tip, the gap of the tip and the gap of the substrate and the gap of the tip, but I will generally assume them to be the same. And so we need an energy of 2 delta. So this happens for voltages equal or larger than twice the superconducting tip. At subgap voltages, current can still flow, tunneling can still occur by Andreev processes. So, for example, we can have 2 electrons tunneling across the junction, forming a Cooper pair in the substrate and leaving behind 2 holes in the tip. Alternatively, you can think of this process as being an Andreev process in which an electron tunnels across and is reflected as a hole. So in this process, we have 2 electrons tunneling across, and both of them gain an energy EV. We create 2 quasi-particles, so we need an energy of twice delta. So this process already happens for voltages equal or larger than the superconducting gap. While it's natural, it may be natural that it's electron pairs that carry the current between superconductors. Of course, it can actually be any number of electrons that are being transferred in these tunneling processes by multiple Andreev reflection. And here is an example of a process that transfers 3 electrons. and this consists of two Andreev reflections. Once the first electron that is tunneling across is Andreev reflected from the substrate, leaving behind a Cooper pair. So this is the Andreev reflected hole. And this hole is again Andreev reflected from the tip, eating up one Cooper pair in the tip, and then coming back as an electron and producing a quasi-particle in the substrate. So in this process, altogether, we have 3 electrons created in the substrate and removed 3 electrons from the tip. And so the 3 electrons that are tunneling across each gain a energy equal to the bias voltage. And we are creating 2 quasi-particles, so they require an energy twice delta. So this process already occurs when the voltage is larger than twice the gap divided by 3. And this, of course, one can continue and transfer even more electrons. And eventually, at very low bias, we need to remember that the Cooper pairs of the 2 superconductors are also Josephson coupled with one another. And this leads to processes which do not create any quasi-particles, either neither in the tip nor in the substrate. And this is dominating transport at small voltages. So with this zoo of processes that are occurring between the superconducting tip and the superconducting substrate, it would of course be nice to have a probe that directly tells you how many charges are involved in the tunneling process. Now, one possibility to do that would be to do shot noise measurements, or even look at the full counting statistics, and that's something that Wolfgang Belzig, for example, looked at quite a few years ago, theoretically. But a simpler possibility is to look at photon-assisted tunneling, and these are the kinds of experiments that Katharina's group has been doing. So ultimately, of course, the interest is to do this photon-assisted tunneling and analyze the tunneling processes for specific or individual subgap states associated with individual magnetic impurities, so individual Yu-Shiba-Rusinov states, for example, or ultimately maybe for the Majorana bound states. And in fact, these measurements yield intriguing and interesting results, shown here for 2 different junction conductances. And one thing you may notice right away is that there is an interesting bias asymmetry between positive and negative biases. And in fact, our theory reproduces these kinds of results very nicely. But it's still quite useful to first go back and look more carefully at the data in the absence of the magnetic impurity, just between 2 plain superconductors, and understand what's going on in that case. So let's start with single electron tunneling. That simply leads to this well-known coherence peaks for due to the superconducting gap edge. And if that's what you observe in the absence of the high frequency radiation, if you now apply high frequency radiation, 40 gigahertz in this case, then these peaks start to split up into sidebands. And the larger the amplitude of the high frequency radiation, the more of these sidebands appear, and they spread out over a wider region. This is nicely seen in this color scale plot of the differential conductance as a function of the sample bias, the bias voltage applied to the junction, and the amplitude of the high frequency radiation. And what you see is that there is many sidebands, and these sidebands split up into these cones as the amplitude of the high frequency radiation increases. And in order to understand that, it's useful to look again in energy space. So the single electron tunneling, these coherence peaks occur because single electrons are tunneling between the occupied BCS peak of the tip, say, and the empty BCS peak of the substrate. And now, once one applies the microwave radiation, then the tunneling electron can also absorb or emit a certain number of photons, and this leads to current even when the two coherence peaks are not aligned but are displaced by a certain number of photon energies. So the tunneling electron now not only gains the energy EV from the bias voltage, but also emits or absorbs any number of photons, and that combined has to give the energy of the two created quasi-particles to delta. Moreover, the maximum number of photons that can be absorbed or emitted is just given by the amplitude of the high-frequency radiation, and that explains why one gets these cones opening up as in this way as the amplitude of the high-frequency radiation is increased. And this relation tells us that the spacing of the sidebands will be just multiples of h bar omega. And if you look at the data, this is in fact what's happening. Now, this was first looked at a long time ago by Tien and Gordon, and they related the conductance of the junction in the absence of the high-frequency radiation to the conductance in the presence of the high-frequency radiation as a sum over all these sidebands, and the strength of these sidebands is just given by these Bessel functions squared. Very similar experiments can be done at the Josephson peak. So now we're at low biases. This is the Josephson peak in the absence of any high-frequency radiation, and this peak also splits up into sidebands as one applies the microwave radiation, and one sees a similar V-shaped pattern. But now the spacing between these sidebands is no longer given by h bar omega, but by h bar omega over 2. And this directly reflects the fact that now at the Josephson peak, it's electron pairs that are being transferred across the junction. So these electron pairs gain an energy twice EV from the bias voltage. They can again absorb or emit any number of photons. And then you see that the spacings will be given by h bar omega over 2. And this kind of cone is again very nicely represented by a more general Tien-Gordon-like expression, except that now we have to replace the electron charge E by twice the electron charge, reflecting the fact that it's basically Cooper pairs that are tunneling across the junction. Now, quite generally, tunneling this sideband spacing gives us an idea about the number of electrons that are tunneling across the junction, and this can be understood based on the Born series for the T matrix in powers of the tunneling Hamiltonian. And the basic idea is just that in many of these processes, the intermediate states, say after you transfer one electron from one side to the other, has a rather high energy, 2 delta in the case of the Josephson coupling. And that makes these intermediate Green's functions basically frequency independent and thus local in time. And then these time-dependent factors that are associated with the energy change of the tunneling electron when it tunnels across the junction, they will simply combine with one another and give you multiples of the same phase factor. And then a simple Fermi-Golden rule calculation would reproduce this Tien-Gordon-like expression with the multiple charges appearing rather than the single electron charge. So this really works. So for example, you can also measure the first Andreev reflection. This is shown here. It's the second derivative because the signal is rather weak. And you indeed find that the sideband spacing in this case comes out as h bar omega over 2 associated with the fact that it's now 2 electrons that are going across the junction. But of course, the real interest is what happens once one puts a magnetic impurity into the system and one has tunneling into an individual bound state, Yu-Shiba-Rusinov state associated with this impurity. And so we've already heard about this before the break. This impurity induces a subgap state. In the simplest model, these subgap states just give you isotropic bound states. In real life, these bound states can be more complicated, and the electron wave function and the whole wave function of these bound states can be quite different. But these are details that are not terribly important for the present talk. What is clear from the understanding that we've developed is that if you tunnel into a subgap state, then presumably this simple Tien-Gordon approach will no longer work. And that is simply because now the energy denominators associated with the resonance behavior of these bound states imply that that these energy denominators are no longer large or energy independent. And thus, this argument that I gave for why these phase factors just multiply each other will no longer be valid. Moreover, it's also clear that now there will be several possible tunneling processes. So imagine that the first electron is tunneling across. This electron cannot leave the junction region because there are no electron states available within the gap. And thus it has 2 different possibilities. Either it waits until a phonon comes along or some other or photon that gives it enough energy to get promoted into the quasi-particle continuum, and then it can leave the junction region. This gives you single electron tunneling, and it requires a bias of delta plus the subgap state energy. Or alternatively, the electron waits until a second electron comes along, or alternatively, it's reflected as a whole and forms a Cooper pair in the substrate. And this is a process which we call resonant Andreev tunneling. It has the same threshold voltage of delta plus the subgap energy. It's clear that this process will be dominant if you have a very small junction conductance, because then it's more likely for this electron to be for a phonon to excite this electron into the continuum, then that another electron will tunnel into the substrate. And this process should be more dominant at larger junction conductances. And in fact, if you now do this photon-assisted tunneling experiment, first at a very small junction conductance, given here, then in fact you see that there are these V-shaped structures. And if you analyze the sideband spacing, that sideband spacing comes out to be h bar omega over E, consistent with the expectation that at small junction conductance, there should be single electron tunneling. It becomes more confusing, perhaps, or intriguing when doing the same experiment at high tunneling conductance. Indeed, things look quite different. For example, there's no longer a V-shape at negative biases, but something that we refer to as a Y-shape. But then if you analyze the sideband spacing, you're in for a surprise, because it turns out to be equal to h bar omega, despite the fact that one expected that there would be a 2-electron process going on in the system. So there are 2 puzzles here. What is the origin of the Y-shape, and why is the sideband spacing actually h bar omega over E rather than h bar omega over 2E? Okay, so in order to resolve this puzzle, we did a little Keldysh calculation, but this Keldysh calculation doesn't fit into a 25-minute talk. So I'll just skip it. It also gives a rather simple result, and which actually can be interpreted easily, but still let me focus on the physics and not look too much at the equations. But to first convince you that this actually works, here is again the data, small junction conductance, large junction conductance, and here are these the results of this theory, just using a couple of parameters which we in fact knew even before Katharina's group did this experiment, and the agreement is rather nice, including this Y shape. So the theory seems to work quite nicely. So then, why does this occur? Here, let's look at this resonant Andreev process again. So here is the process in the absence of the microwave radiation. Let's focus first on the electron tunneling across. So the threshold is when the coherence peak of the tip is lined up with the energy of the subgap state in the substrate. And if we now one now applies microwave radiation, again, this tunneling electron can emit or absorb photons, and so this threshold will open up into this kind of cone. But in principle, now you can also think of a second cone, namely for the hole. That whole process would already be resonant at a smaller bias. We could shift this whole thing up by twice epsilon naught, and then the hole would be in resonance with this BCS peak. So actually, this whole resonance would start here, and then once we apply the microwave radiation, then this actually also opens up into a cone. Now, tunneling, of course, can only occur when both electron tunneling and hole tunneling is possible, and this is not the case in this region. There, only hole tunneling is possible, and it's not the case on the other side here, where there's only electron tunneling possible. So we don't expect to see any visible thresholds in these two regions. But we do expect to see thresholds in this region, because here hole tunneling is possible, and here electron tunneling is possible. But we would only see the electron thresholds here, because there are no hole thresholds outside of this region. And here we would only see the hole thresholds and no electron thresholds. But finally, in these overlap regions where these two cones overlap, we would expect to see both the electron thresholds and the hole thresholds. And same here at negative bias. So that kind of suggests what might be going on here. So if you compare this, then this line is just this line of the whole cone, and but then this line turns out to be this line, and for some reason one is actually not seeing all these whole thresholds down here. At positive biases, we see just the usual V shape. So this is just this these electron thresholds. But for some reason, there is no difference between the thresholds here and the thresholds here. So there's not another region here where there's more thresholds than down here. In order to understand that, we have to notice that actually the electron and the hole wave function of this Shiba state are very different. So here are some data just in the absence of the microwave radiation, and just looking at the resonances, and you see that the hole resonance is much stronger than the electron resonance. And this means that the hole tunneling amplitudes are actually, the tunneling rates are actually much larger than the electron tunneling rates. And as a result, it turns out that if you now look again at these processes, these electron tunnelings are in some sense much slower. They are rate limiting in a somewhat simplistic way of saying it, compared to these hole tunneling rates, which are much faster. And it's the rate limiting process that one ends up seeing. So it actually turns out that both for positive biases and for negative biases, one is actually only seeing the electron thresholds, and that is why there are no two sets of thresholds showing up in some region here. We just generally, one just generally sees the electron thresholds. The only exception from this is right here, where hole tunneling just barely sets in and is still equally fast as electron tunneling, and this is why one sees this entire line of thresholds of the edge of these hole thresholds here. And in fact, if you look closely here, there's kind of a double structure that doesn't fit any regular pattern, and that's precisely because there is electron and hole thresholds kind of coming in the same region. So all of this is nicely explained then both by noticing that there are separate thresholds for electrons and holes, and the fact that this Shiba state is very asymmetric. Okay, so here then is theoretical results, which you can do for any parameters. So here, this is equal electron and hole wave functions. This is whole electron wave functions being much smaller than hole wave functions. This is electron wave functions being much larger than hole wave functions. And then in this direction, we are changing the subgap energy relative to the high frequency radiation. And you see that, for example, the Y on the left-hand side has this shape, but if you reverse electron and hole wave functions, then the Y kind of inverts and comes in on the other side. If you have equal electron and hole wave functions, then you indeed see more thresholds within this region where you would expect both electron and hole thresholds to show up. Now, this one interesting application of this would be to Majorana bound states. Majorana bound states have U equal to V, and ideally they should have an excitation energy, subgap energy of equal to 0. So this is basically what you would expect up to some scaling factor of 2. This is interesting because if you probe Majoranas with a superconducting tip, then the Majorana peak actually appears not at 0, but at voltage equal to the superconducting tip gap. And so to really be sure that this is a zero energy state, you need to subtract two large numbers from one another, the voltage at which you're measuring your resonance and the tip gap. And if you subtract two large numbers to get a small number, you're likely to make, or it's prone to errors. And it would be nice to see this subgap energy directly as a line splitting in your experiments. And in fact, this is what this suggests. So imagine that you're not dealing with a Majorana, but with a subgap state that happens to have U equal to V. Then if you look at these photon-assisted tunneling patterns, then you would see this splitting directly in your data. So this is shown slightly larger here. These line splittings are now appearing because the thresholds for electrons and holes are no longer exactly on top of each other, and you can, in this way, sort of at least show that it's not a Majorana, because you can see the finite energy of the subgap state without subtracting two large numbers from one another. And that might be quite a sensitive way of making sure that you're not dealing with Majoranas. Okay, so of course, if you do this with an SDM, you also know that Majoranas should have equal electron and hole wave functions for any position, but accidental E equals 0 subgap states would have different energies. And so by looking around, you can look for regions where they differ or where they are equal, and this gives you additional information. So with that, I'm at the end of this talk. Photon-assisted tunneling reveals the different tunneling processes in the superconducting SDM junctions at the atomic scale. the theory needs to go beyond that simple Tien-Gordon approach, but agrees very, very nicely with the experiment. And photon-assisted tunneling provides a sharp probe of Majorana's, and maybe it can make the golden path even more shiny. Thank you for your attention.